Welcome to Relax Story, a peaceful place where gentle stories help you leave behind the worries of the day and drift into a calm, restful sleep. Each soothing narration is designed to relax your mind, ease tension, and bring a sense of comfort and peace. If you enjoy listening, please like and subscribe, and feel free to share your thoughts or story suggestions in the comments. Now, close your eyes, take a slow, deep breath, and let Relax Story guide you into a night of deep and peaceful sleep. It often begins with an anonymous creature. Perhaps it was carried out to sea on a raft of drifting vegetation. Perhaps its ancestors crossed a strip of land exposed when sea levels fell during an ice age. Sometimes all it took was a storm, an ocean current, or a narrow stretch of water crossed during a rare moment in history. Journeys like these happened again and again throughout the Quaternary period, as advancing and retreating ice sheets repeatedly pushed the seas forward and pulled them back. Each shift in the water left certain populations cut off from the rest of the world. Island evolution does not begin with a new species. It begins with an old population becoming isolated. But isolation is only the first door. Inside an island, the familiar rules slowly begin to change. Living space becomes smaller. Food is different. There are fewer species. Predators that once inspired fear may be gone. Competitors that were once everywhere may no longer exist. In a world like this, the traits that once made a creature successful on the mainland are not necessarily the traits that matter anymore. Small size is no longer an absolute advantage when there is little left to flee from. On the other hand, a large body can become a burden when resources are too scarce to support it. And this is where something strange begins to emerge. Biologists call it the island rule. Across many isolated islands, small species often tend to grow larger over time. Large species, meanwhile, often become smaller. Evidence of this pattern appears in mammals, birds, reptiles, and even some groups of amphibians. What makes it so remarkable is that the same evolutionary process can produce two completely opposite outcomes. One island may give rise to giant rats. The very same kind of environment may also create dwarf elephants. Evolution is not trying to make life bigger or smaller. It is simply making constant adjustments, shaping living things to fit the conditions that exist around them. On the mainland, animals face countless pressures all at once. On islands, there are fewer pressures, but each one carries greater weight. A seemingly minor change can reshape the form of an entire lineage over thousands of generations. If islands truly have the power to alter the size of life itself, one question almost immediately follows. Why are the smallest creatures so often the first to start growing larger? The answer waits among the islands of Southeast Asia, where certain species of rats embarked on an evolutionary journey far stranger than most of us would ever imagine. In the seas east of Indonesia lies a chain of islands scattered like stepping stones between two worlds. To the west is Asia. To the south and east is Australia. The vast region between them is known as Waleka, one of the most remarkable places on Earth for evolutionary researchers. Here, islands do more than separate land masses with water. They separate populations with time itself. Within the relatively compact Lesser Sunda Islands, also known as Nusa Tenggara, creatures once emerged that seemed to belong to entirely different worlds. There were Komodo dragons that rose to become the dominant predators of an entire archipelago. There was Homo floresiensis, so small that many people compare it to something out of a fairy tale. There were ancient elephants reduced to astonishingly tiny sizes. And here as well, rats moved in the opposite direction. Amid all these evolutionary paradoxes, a quiet question begins to take shape. What happens when a rat lives in a world where most of the creatures that hunt it are no longer there? To find the answer, the journey leads us to Alor, an island on the eastern end of the Lesser Sunda chain. Along its southwestern coast lies an ancient cave known as Makpan, within layers of sediment accumulated across countless generations. Small skeletons rested undisturbed for thousands of years before revealing a remarkable secret. The animal was named Alormis aplini. At first glance, it still looks like a rat. But the closer it is examined, the more that familiarity begins to fade. It was significantly larger than the common ratus species we know today. The difference was so substantial that researchers concluded it was not merely a new species, but an entirely new genus, which they named Alormis. Even more intriguing, Alormis aplini was not alone. On Flores, there was Papagomes, another group of giant rats. On Timor, researchers found Millimongamis. Across several other islands in the same chain, unusually large rat lineages appeared again and again. When all of these discoveries are placed side by side, a pattern begins to emerge. It is as though every island is telling the same story through different characters. The story is not really about how to become larger. The truly fascinating question is why becoming larger became an advantage in the first place. The distant ancestors of these rats were most likely small rodents, not very different from the countless species living across Southeast Asia today. On the mainland, being small is a precious gift. It allows an animal to slip through spaces predators cannot reach. It provides shelter within dense vegetation. It enables rapid growth, early reproduction, and astonishingly fast population recovery. Every day on the mainland is a continuous escape. Above, birds of prey search with sharp eyes. On the ground, snakes wait. In the undergrowth, small carnivores are always looking for an opportunity. Even food must be shared with countless competing rodents. In such a world, small size often means survival. Then, a small population becomes isolated on an island. The sea quietly raises barriers that few predators can cross. Many specialized enemies disappear from the equation. Some competitors vanish as well. The pressures that shaped these animals for millions of years begin to weaken. Suddenly, being small is no longer the overwhelming advantage it once was. When fear no longer dominates every decision made by nature, evolution begins optimizing for different needs. On islands, food supplies are not always reliable. Dry seasons can last for long periods. Resources can decline without warning. Under these conditions, a larger body offers better energy storage. It allows an animal to endure longer stretches without food. It opens access to a wider variety of resources and makes it easier to exploit food sources that smaller bodies cannot use efficiently. There was never a moment when a rat suddenly became a giant rat. The transformation happened so gradually that no generation could recognize the change within itself. Each generation grew only slightly larger than the one before it. The difference would have been almost impossible to notice during a single lifetime. Yet after thousands of generations, the distance between the island descendants and their mainland ancestors became unmistakable. That is the moment when a rat no longer looks entirely like the rat we think we know. Perhaps the most important thing to remember is that these animals did not become larger because they grew more aggressive. They did not become larger because they possessed extraordinary strength. They became larger simply because the new environment allowed that evolutionary path to persist and be preserved over time. And this story is not unique to rats. On islands around the world, gigantism has appeared in lizards, insects, and many other groups of small animals. Each case contains its own details, but all share a familiar pattern. They begin with a small body. They enter an isolated environment. Predation pressure declines. Competition changes. Then size gradually shifts in a new direction. These examples remind us of something that is surprisingly easy to forget. Many traits that humans think of as fixed characteristics of a species are often nothing more than responses to particular living conditions. Even the size of a rat is not a constant written permanently into nature. On the mainland, rats are remembered for their ability to hide and flee. Their lives are shaped by whatever is pursuing them each day. On islands, that definition begins to blur. When familiar pressures disappear, life gains an opportunity to experiment with different possibilities. Sometimes the first change is not behavior, not fur color, not feeding habits. Sometimes it begins with the shape of the body itself. But if the disappearance of predators can cause a rat to grow larger over countless generations, the other side of the island rule holds something even harder to believe. There are creatures that begin as giants. They arrive on islands, and those very islands begin making them smaller. That is where we encounter elephants diminished by the sea itself. There is something deeply paradoxical about imagining an elephant stepping onto a small island in the middle of the Mediterranean. Its body was built for vast open plains, for long journeys across grasslands, for endless days spent searching for vegetation across landscapes that seemed to stretch forever. And yet, during the ice ages of the Pleistocene, when sea levels rose and fell with the cold and warm rhythms of the earth, some populations of ancient elephants found themselves stranded on islands such as Sicily, Malta, Crete, and Cyprus. At first, they were no different from their mainland relatives. They belonged to the lineage of Paleoloxodon antiquus, the European straight-tusked elephant, a species that could stand nearly 4 meters tall. Even beside a modern elephant, they would have been awe-inspiring creatures. Their long tusks, massive bodies, and enormous energy demands were traits that had helped them thrive in the expansive world of the continent. Then time began doing what it does best. Thousands of years passed, then tens of thousands. The islands gradually became separated from the mainland by rising seas. The elephants no longer had any path back to the lands where their ancestors had once roamed. They were confined to a world with shorter horizons, fewer trees, and limits their ancestors had never known. The result was almost impossible to believe. On Sicily and Malta, a form known as Paleoloxodon falconeri emerged. Fully grown individuals often stood only about 1 meter tall, or even less. A creature descended from a lineage of giants had become roughly the size of a large calf, without knowing their shared ancestry. An observer might easily assume they were entirely unrelated animals. The transformation did not happen because nature wished to create a strange, miniature version of an elephant. It emerged from a remarkably simple conflict. On the mainland, a large body is an obvious advantage. It allows elephants to travel farther in search of food. It enables them to consume enormous quantities of vegetation each day. Their size also discourages many predators. In continental ecosystems, becoming a giant herbivore is often a highly successful strategy. But islands do not operate by the same rules. Space becomes smaller. Plant resources become finite. Fresh water is not always abundant. Extended dry seasons can quickly turn survival into a competition for limited resources shared by every living thing on the island. The larger the body, the larger the daily energy bill. That is when an old advantage begins to become a burden. Fossil evidence suggests that the smaller or more isolated an island was, the more extreme the dwarfing of its elephants tended to be. It is almost as if the island itself quietly participated in shaping the size of the creatures that lived there. No sudden crisis was required. No catastrophic disaster had to occur. Thousands of years of repeated resource limitations were enough for nature to begin adjusting bodies toward greater efficiency. From that moment on, the island was no longer merely a place to live. It became a filter operating across countless generations. At first, the isolated elephant populations still looked much like their ancestors. Every individual required vast amounts of food to maintain its body. During periods of scarcity, however, smaller individuals gained a subtle advantage. They needed less energy. They survived more easily when vegetation became limited. They faced less pressure in a world bounded by coastlines. Those individuals survived slightly more often. They reproduced slightly more successfully. Traits associated with smaller size were passed on with increasing frequency. There was never a single moment that marked the change. No elephant woke up one morning and realized it had become smaller than its ancestors. The process unfolded so gradually that each generation would have barely noticed. Yet when viewed across tens of thousands of years, the outcome becomes as clear as a completed painting. A lineage that once ranked among the largest animals in Europe had become one of the smallest elephant forms ever known. Their body mass shrank to only a fraction of that of their mainland ancestors. The same evolutionary heritage, yet two forms that appeared almost opposite in scale. What makes the story even more fascinating is that this reduction in size did not turn them into fast-living animals. When researchers examined the microscopic structure of the bones of Paleoloxodon falconeri, they discovered something unexpected. These dwarf elephants still carried the slow pace of life characteristic of elephants. They reached maturity at around 15 years of age and could live for nearly 7 decades or more. It is a beautiful contrast. The body became smaller, but the clock inside the body continued to tick like that of an elephant. The island did not transform them into small animals in the ordinary sense. It did not erase the evolutionary history of their ancestors. It simply adjusted the traits most necessary for survival within a new set of limits. The result was a more economical version, a more suitable version, yet one that still carried the fingerprints of the past. Sicily and Malta are only the most famous examples within a much larger picture. Across the Mediterranean, islands preserved countless miniature versions of giant animals. Cyprus had its own dwarf elephants. Crete once hosted dwarf elephants and dwarf mammoths. Several islands throughout the Aegean left behind traces of ancient elephant populations that followed a remarkably similar path. And the phenomenon did not stop with elephants. Dwarf hippos once lived on islands. Some ancient deer populations also became dramatically smaller. Many large animals seemed to confront the same question when they entered the island world. Did they truly need to carry all of their former size with them? Whenever the answer was no, evolution returned to its familiar work. At this point, the other side of the island rule begins to reveal itself more clearly. While small animals often grow larger when predation pressures diminish, giants frequently move in the opposite direction. Energy, fresh water, and space become invisible boundaries that force bodies to change. On the mainland, enormous size had once been a source of power. On islands, that same size became a cost. A creature built for immense landscapes found itself compressed into a world surrounded by water. The traits that had once ensured success became the very things that needed to be reduced. Evolution does not preserve greatness simply because it was once useful. It does not keep size, strength, or form as a memorial to the past. Across millions of years, it seems to ask only one quiet question: does this body still fit the place where it lives? On a small island surrounded by sea, sometimes the only way for a giant creature to continue existing is to become smaller than its own history. But not every large animal was diminished by island life. One reptile entered the island world and followed a very different path. It kept its formidable size. It occupied the vacant space left behind by large predators. It rose to the very top of the food chain across an entire archipelago. That is the story of the Komodo dragon. Amid the vast blue waters of Indonesia lies a cluster of islands that, at first glance, hardly seem like the kind of place capable of supporting giant predators. Komodo, Rinca, Flores, Chili Motang, and Gili Dasami are simply isolated pieces of land scattered across the Lesser Sunda region. They belong to Wallacea, a remarkable transition zone between the biological worlds of Asia and Australia, where invisible boundaries of evolution cut across the ocean. For millions of years, deep straits kept these islands separated from one another. Even during ice ages, when falling sea levels exposed large stretches of land, many of these channels remained deep enough to prevent animals from moving freely between islands. This long isolation transformed Wallacea into a vast natural laboratory, where each island quietly wrote its own evolutionary story. At first glance, the region seems to lack nearly every condition needed to support an apex predator. There are no tigers, no lions, no packs of wolves roaming open grasslands. Resources are more limited than on the mainland, and the available habitat is far smaller. Yet it is here that a creature more than 3 meters long stands at the very top of the food chain, like an ancient king who never surrendered his throne. That creature is Varanus komodoensis, better known as the Komodo dragon. It is the largest living lizard on Earth. An adult male can exceed 3 meters in length and weigh between 70 and 90 kilograms under natural conditions. Exceptional individuals can surpass 100 kilograms, giving them the appearance of creatures from a much older world rather than modern reptiles. What makes the Komodo dragon such a fascinating character is that it does not fit neatly into the patterns we have seen so far. Island rats grew larger from tiny ancestors. Island elephants shrank from giant ancestors. The Komodo dragon belongs entirely to neither story. For decades, researchers debated the origins of its immense size. Did isolation on islands transform it into a monster? Or had it always been large? Fossils discovered in Australia gradually revealed a different answer. Long before the modern Komodo dragon appeared, giant lizards from the same lineage already roamed the vast landscapes of the southern continent. That realization completely changed the way we understand this animal. The Komodo dragon is not a small lizard that happened to become gigantic on an island. It is the surviving descendant of a giant family that was once far more widespread. While many branches of that lineage vanished over time, this one endured, a living memory of a world that has long since disappeared. A body of that size comes with enormous energy demands. On small islands, that would seem almost impossible to sustain. The answer lies in the animals that share its habitat. Herds of Timor deer, moving through the dry grasslands, provide one of its most important food sources. They are a crucial link in the chain that allows this giant predator to survive. Every step taken by a deer herd also helps maintain the balance of the island ecosystem. Wild pigs serve as another major source of prey for adult dragons. On some islands, water buffalo introduced by humans in recent centuries have become part of the landscape as well. Elderly, injured, or weakened buffalo occasionally become targets. The Komodo dragon does not maintain its dominance in isolation. Its survival is closely tied to the presence of hoofed mammals and other large sources of food. Yet prey populations on islands are always limited. A giant predator cannot afford to waste energy on long pursuits. That reality helped shape one of the most effective hunting toolkits in nature. Almost constantly, a Komodo dragon flicks its forked tongue in and out of its mouth. Many people interpret this behavior as a sign of aggression. In reality, it is reading invisible signals drifting through the air. Each flick gathers countless chemical particles, which are then delivered to the Jacobson's organ inside the mouth. To a Komodo dragon, the air is like an enormous book. It can detect carrion or traces of prey from remarkable distances. In an environment where food does not always appear in plain sight, this ability saves an enormous amount of energy. Rather than searching blindly, it allows scent itself to guide the hunt. When the right moment arrives, the dragon reveals another form of intelligence. It does not run for kilometers like wolves. It does not maintain long, high-speed chases like cheetahs. Most of its time is spent waiting. A motionless body blends into the color of dry earth. Its eyes track every movement. Then, when prey enters the right range, the entire animal explodes into action for a few brief seconds. For many years, the Komodo dragon's famous bite was believed to be dangerous primarily because of bacteria in its mouth. Modern research has revealed a far more sophisticated mechanism. Venom glands help lower blood pressure, increase bleeding, and accelerate the weakening of the victim. Victory comes not through superior speed, but through patience, precision, and the ability to outlast its prey. Yet perhaps the darkest aspect of the Komodo dragon emerges within its own life cycle. An adult dragon may prey upon younger members of its own species. From the moment they hatch, young Komodos face the most dangerous threat they will ever encounter. They quickly climb into trees and spend their early years among branches high above the ground. Their world becomes one of trunks, leaves, and open air. It is not completely safe, but it is far safer than the landscape below. What makes this especially remarkable is that the predator they fear most is not an eagle circling overhead, not a snake hidden in the brush. It is the adult Komodo dragons wandering beneath them. A strange life cycle emerges from this reality. Childhood belongs to the trees. Adulthood belongs to the ground. The species' adaptability goes even further. Under certain circumstances, a lone female can produce offspring without a male through a process known as parthenogenesis. On isolated islands, where distance can separate small populations for long periods, this ability functions almost like a backup plan, quietly preserved by evolution. The Komodo dragon exists not only in biology, but also in local memory and tradition. One long-standing legend tells of twins born at the same time. One was born in human form. The other was born in the form of a dragon. Their lives followed different paths, yet they remained members of the same family. Perhaps that is why many island communities do not view Komodo dragons merely as dangerous beasts. They are often regarded as ancient residents who existed long before the current generations arrived, creatures deserving respect more than conquest. The Komodo dragon challenges a common intuition about island evolution. Not every island produces smaller animals. Not every large body must shrink over time. Sometimes islands do not create monsters. They simply become the last places where ancient monsters survive. When a world disappears, its traces do not always vanish with it. Sometimes they retreat into small fragments of land scattered across the ocean. On those fragments, the past continues to breathe in living form. The Komodo dragon is like a rare doorway that remains open, leading back to an age that most of the world has forgotten. And if the Komodo dragon is proof that a creature can preserve its ancient power through millions of years of isolation, the next journey leads to an entirely different outcome. Some animals arrived on islands and gradually abandoned the very ability that once allowed their ancestors to conquer the skies. That is the story of birds that forgot how to fly. A bird standing on the ground with its wings folded neatly against its sides seems to suggest something almost obvious. Given a single moment, it could launch itself into the air, rise above trees, cliffs, or open sea. Wings feel like a promise that the sky is always there, waiting as an escape route. And yet, on many isolated islands around the world, from New Zealand and Mauritius to Hawaii, the Galapagos, and Aldabra, some birds gradually abandoned that promise. What makes this so remarkable is that it did not happen only once. Across different eras, on islands separated by thousands of kilometers of ocean, many groups of birds arrived at the same destination. Their ancestors could fly. They belonged to lineages that had crossed vast stretches of water to reach distant islands. But over countless generations, that ability weakened, faded, and in some cases disappeared altogether. If flight is one of evolution's greatest achievements, why did so many island birds move in exactly the opposite direction? The answer begins with a fact that often goes unnoticed. Flight is not a free gift from nature. It is one of the most expensive activities an animal body can perform. To leave the ground, a bird must carry an entire system built specifically for flight. Massive chest muscles constantly consume energy to generate lift. The skeleton must remain so light that many of its internal structures become hollow. Metabolism must run at a high rate to ensure instant takeoff whenever danger appears. Many other anatomical features must serve the demands of the sky rather than the countless other needs of life. All of those costs make sense only when flight provides rewards large enough to justify them. Wings are worth keeping if they help a bird escape predators, find food, or reach safer places. As long as the benefits outweigh the price, evolution continues to preserve the ability. But on many ancient islands, that equation began to change. Before humans arrived, countless islands were relatively peaceful worlds for birds. There were no cats waiting in the undergrowth, no wild dogs pursuing them across open grasslands, no foxes or weasels specializing in hunting ground-dwelling birds. In many island ecosystems, the need to take flight in order to survive almost disappeared. Generation after generation, birds lived in environments where walking was enough. They no longer needed to burst into the sky whenever they sensed danger. They no longer needed to maintain an expensive biological machine to respond to threats that rarely appeared. And so natural selection quietly shifted direction. Individuals that conserved energy a little more efficiently gained a slight advantage. Those that foraged more effectively on the ground gained another. Birds that could run farther or move more efficiently across the landscape gained one as well. Over thousands of years, those tiny differences accumulated. Chest muscles gradually shrank, skeletons changed, wings became shorter, the ability to fly weakened. Eventually, for some species, the sky was no longer where they belonged. New Zealand offers one of the clearest examples of this process. Within the ancient forests of those islands lives a remarkable creature known as the kakapo. At first glance, it still looks like a parrot, complete with a curved beak and fully formed wings. Yet the kakapo is the only parrot in the world that cannot fly at all. Its body is larger than that of most of its relatives. It is also the heaviest parrot still alive today. During the day, kakapos usually remain hidden in darkness. Only after nightfall do they begin their slow wanderings through the forest. An individual can live for many decades, sometimes approaching a full century. The ancestors of the kakapo could fly just like other parrots. But in ancient New Zealand, where land predators were almost entirely absent, the pressure to maintain flight steadily declined. Over time, their bodies grew larger. Their climbing abilities became more important. Energy was redirected toward growth and reproduction instead of supporting a massive flight apparatus. The most important lesson lies in how we choose to view that change. The kakapo is not an example of failure. It did not lose flight because it was somehow inferior. It simply became perfectly adapted to the world in which it lived. In that world, the ground mattered more than the sky. And the kakapo was far from alone. Across island ecosystems, many different groups of birds arrived at similar solutions. Rails provide one of the most striking examples. On islands scattered across the globe, different rail species repeatedly evolved toward flightlessness despite being separated from one another. In New Zealand, the weka became a bird deeply tied to life on the ground. The takahe, now one of the archipelago's most celebrated species, was once believed to have vanished forever before being rediscovered in remote mountain regions. Further back in time stood the moa, a group of giant birds that once dominated New Zealand. Some species could exceed 3 meters in height when fully extended, yet none of them could fly. Far away in the Indian Ocean, on the island of Mauritius, an ancient pigeon followed the same path. That bird was the dodo, a creature whose story will unfold in the next chapter. What makes all of this truly astonishing is that these birds were not closely related. They emerged from different evolutionary lineages and different origins. Yet when faced with similar environmental conditions, they repeatedly arrived at nearly identical outcomes. That is the great paradox of this chapter. On the mainland, wings are often an escape route. On islands, wings can become an unnecessary expense. Evolution does not care whether a trait appears beautiful. It is not impressed by how spectacular a behavior may seem. Nor does it preserve a feature simply because that feature was enormously successful in the past, generation after generation. Only a much simpler question is tested. Is it still useful? That is why one of nature's greatest inventions can disappear if the environment no longer demands it. People often imagine evolution as a constant process of accumulating new abilities. Yet many of the most important moments in the history of life move in the opposite direction. Evolution is also the art of letting go, removing what is no longer necessary, keeping only what truly serves survival. Not every change is an addition. Many of the greatest transformations begin with a loss. In the vast world of living things, what survives the longest is rarely the strongest or the most complex. More often, it is simply what fits its environment best. But forgetting the sky was only a biological change. The real tragedy began when another world arrived on those islands, a world that brought rats, cats, dogs, and pigs. Above all, it brought humans. And that was the moment that sealed the fate of one of the most misunderstood birds in history, a creature that was never foolish at all. It had simply lived for too long in a world that felt safe. There is a strange paradox hidden in the southwestern Indian Ocean. A bird survived countless rainy seasons, endless droughts, and tropical storms that swept across the sea for millions of years. It watched its island change slowly and almost imperceptibly through the passage of geological time. And yet that same bird disappeared within just a few decades of its first encounter with humans. The island was called Mauritius, lying about 900 kilometers east of Madagascar, surrounded by vast stretches of ocean. Mauritius was once a world almost completely separated from the rest of the planet. There were no cats lurking in the undergrowth, no hunting dogs roaming the ground, no foxes, weasels, or large predators of the kind commonly found on continents. Within that long silence, carried across countless generations, a remarkable creature emerged. It was the dodo, the bird known scientifically as Rufus cucullatus, later destined to become one of the most famous symbols of extinction in history. For centuries, the name dodo became linked with images of clumsiness and stupidity. Old illustrations portrayed it as a heavy, awkward creature, seemingly too foolish to survive. Over time, even the word dodo itself became a form of ridicule. The reality was very different. The dodo was not a primitive bird trapped in the past, nor was it an evolutionary mistake. The genetic traces that remain reveal that its closest relatives are the pigeons that can still be found throughout the modern world. That single fact changes everything about how we see this bird. To reach Mauritius, the dodo's ancestors had to cross hundreds, perhaps even thousands, of kilometers of open ocean. Such a journey could only have been accomplished with wings. The dodo was not born on the ground. Its ancestors were travelers of the sky. Long before humans arrived, a population of flying birds from a distant mainland or neighboring island chains somehow reached Mauritius. What they found was a world unlike anything they had known before. No predators waiting behind them, no desperate escapes, no relentless struggle for survival of the kind that shaped life on the continents. In that environment, the rules began to change. On the mainland, flight is one of the most important tools for survival. A single moment of hesitation can mean death. But on Mauritius, wings no longer carried the same life or death importance. Flight is expensive. Muscles must grow larger. Bones must remain lighter. The body must constantly maintain structures that demand enormous biological investment. Once flight became unnecessary, individuals that conserved energy more efficiently gradually gained an advantage. Over thousands of generations, the dodo's body became larger. Its wings grew smaller. Its ability to fly disappeared. To us, that may sound like a loss. To evolution, it was a success. The dodo no longer wasted energy on traits it did not need. It walked across the forest floor, nested on the ground, fed on the resources available in its environment, and reproduced effectively within a stable ecosystem. Every part of its body was suited to Mauritius. There is no evidence that the dodo was struggling before humans arrived. Quite the opposite. It was thriving in its own world. Then one day, sails appeared on the horizon. In 1598, Dutch sailors landed on Mauritius and recorded the existence of the dodo. At first glance, the encounter seemed ordinary enough. A few ships anchored offshore. A few sailors explored the coastline. Yet, in reality, it marked the beginning of a collision between two entirely different worlds. Because humans never arrive alone. From the dark holds of ships came rats. Pigs soon wandered into the forests. Cats appeared with their sharp hunting instincts. Dogs brought a kind of pursuit that Mauritius had never known. Along with them came other introduced species that gradually transformed an ecosystem that had remained stable for millions of years. Suddenly, the dodo's entire survival strategy was turned upside down. Its eggs rested on the ground. Its chicks grew up on the ground. The adults themselves lived entirely on the ground. Everything that had once been an advantage became a vulnerability. The tragedy did not unfold over thousands of years. By evolutionary standards, it happened almost instantly. Rats consumed eggs. Introduced animals preyed upon young birds. Competition for food increased. Forests changed as humans exploited resources. Ecological relationships began to break apart, one link at a time. The dodo had no evolutionary experience with these new pressures. It possessed no suitable defensive behaviors. And most importantly, it had no time. Evolution usually requires many generations to respond to change. Humans transformed an entire ecosystem within decades. By around 1662, the last reliable reports of the dodo appeared. Less than a century after Europeans first described it, the bird that had once dominated its own isolated world vanished from the earth. This is the moment when the story takes on an entirely different meaning. The dodo did not go extinct because it was weak. The dodo did not go extinct because it was slow. And the dodo certainly did not go extinct because evolution got it wrong. Its world simply changed faster than evolution could adapt. For centuries afterward, the dodo remained buried beneath layers of misunderstanding. People mocked it as a symbol of failure. In reality, it was a textbook example of an organism that had become extraordinarily successful through specialization. It was perfectly designed for the environment of Mauritius. Only Mauritius. What killed the dodo was not the present. What killed the dodo was a future that arrived too quickly. Viewed more broadly, its story reveals a deeper law of life. Evolution does not create organisms that are perfect in every circumstance. It creates organisms that are as well suited as possible to the conditions they currently face. The more perfectly adapted a species becomes to a stable world, the more vulnerable it may be when that world disappears. Islands often produce creatures found nowhere else on Earth. Isolation gives rise to evolutionary wonders unlike any others, yet that uniqueness carries a quiet cost. The dodo is not a story about stupidity. It is a story about speed. It is the story of a moment when the pace of evolution and the pace of human history stopped moving together. And when that happens, even creatures that were once perfectly suited to their world can vanish as though they had never existed at all. The dodo was not the only case. It was simply the most famous face among countless similar stories. Across the oceans, islands repeatedly produced evolutionary marvels found nowhere else, and again, sails appeared on the horizon. Soon afterward, those marvels began to disappear. That is when the other side of the island rule reveals itself. When evolution creates something extraordinary, extinction may already have been waiting quietly in the harbor all along. A species may take hundreds of thousands of years to emerge. An ecosystem may need millions of years to find its balance among food, climate, terrain, and countless complex biological relationships. Yet when we look back at the history of the world's islands, the most astonishing question is not what created such strange creatures, but what made them disappear so quickly. People often think of asteroids, volcanoes, or vast ice ages. But in many cases, the first sign that an island ecosystem was about to change was nothing more than a small sail appearing on the horizon. Between the 15th and 19th centuries, as global sea routes expanded at an unprecedented pace, islands that had been isolated by oceans for millions of years began to reconnect with the rest of the world. From Mauritius, Rodriguez, and Réunion in the Indian Ocean to Hawaii in the middle of the Pacific, from New Zealand in the south to Guam, Polynesia, and Micronesia scattered across immense stretches of sea. Every island had its own story. Yet when those stories are placed side by side, the main character is no longer a single species. The main character becomes entire island ecosystems standing before a meeting unlike anything in their history. The dodo is often remembered as the most famous symbol of extinction. This heavy-bodied bird from Mauritius vanished within just a few decades of human arrival. Over time, its image became a familiar reminder of what can happen when a creature shaped in isolation encounters change that comes too fast. But the dodo was never alone in that tragedy. On nearby Rodriguez Island, the Rodriguez solitaire once wandered through forests like a distant cousin of the dodo. It too had never learned to fear predators its ancestors had never known. Soon after humans, cats and pigs arrived. The bird disappeared from the world as well. Far to the south, the forests of New Zealand once trembled beneath the footsteps of the moa. Some species stood taller than a human and filled the role that large grazing mammals occupied on continents. They browsed on leaves, dispersed seeds, and helped shape entire ecosystems. Then, in what was only a brief moment on the evolutionary timescale, those giants survived only as fossilized bones. On many other islands, small rails followed a similar path. Generation after generation, they gradually gave up the ability to fly because flight was no longer necessary for survival. What had once been a perfect energy-saving strategy eventually became a weakness when new threats arrived. The common thread among all these creatures was isolation. They evolved in worlds that were nearly closed systems. They faced few predators. They also never had the opportunity to learn how to deal with dangers that had never existed before. What is remarkable is that in many cases, humans were not the most dangerous predators. When a ship reached an island, it was not only sailors who stepped ashore. Hidden within the dark holes were other passengers. They were so small they were almost invisible, yet powerful enough to alter the fate of an entire island. Black rats and brown rats slipped from the ships and multiplied rapidly. They discovered bird nests built directly on the ground, where eggs and chicks had never faced predators like these before. With each breeding season, a few fewer nests succeeded. To control the rats, humans brought cats. But the cats quickly discovered an island full of slow-moving and unwary prey. Dogs followed human settlements and introduced a level of hunting pressure that had never existed in the history of many islands. Pigs were released as a reserve food source. They rooted through the soil, destroyed vegetation, crushed nests, and transformed habitats that had remained stable for very long periods of time. At the same time, new diseases arrived. Many island bird populations had never been exposed to such illnesses and possessed little ability to resist them. Islands that had been protected by oceans for millions of years suddenly found themselves facing the entire world at once. The pattern repeated itself again and again. A ship appeared. Humans arrived. Introduced species escaped into the environment. They encountered creatures that had never learned fear. Ground nests became easy targets. Eggs lacked special defenses. Chicks had no instinctive response to predators. Survival rates began to fall. Populations shrank year after year. Some species declined so rapidly that they vanished before science had even fully documented their existence. Evolution may require hundreds of thousands of years to create a species. History sometimes needs only a few decades to erase one. Even so, the picture is not entirely dark. On South Georgia Island, one of the largest island ecosystem restoration efforts ever attempted unfolded over many years. Invasive rats and mice that had devastated crown-nesting seabirds were eventually removed. Soon afterward, many bird populations began returning to places where they had once disappeared. On Macquarie Island in the South Pacific, programs to control rabbits, feral cats, and rats also allowed native ecosystems to recover. The calls of seabirds gradually returned to areas that had fallen silent. These successes cannot bring extinct species back, but they reveal something important. The damage humans cause can sometimes be healed if intervention comes soon enough. The greatest lesson of islands is not found in the number of species saved. It lies in what those species reveal about the way evolution works. The paradox of island worlds is that the strangest creatures often do not emerge in the harshest places. They emerge in the most stable ones. It is stability, stretched across thousands of generations, that allows evolution to experiment with possibilities that seem almost impossible. It allows birds to forget the sky. It allows rats to become giants. It allows elephants to shrink to miniature sizes. Yet that same stability leaves many species unable to respond when the world changes too quickly. The very thing that makes island creatures extraordinary is also what makes them fragile. Evolution does not create invincible organisms. It creates organisms suited to the world they inhabit. Sometimes the greatest threat is not a stronger predator. It is the sudden arrival of an entirely different world. Before sails appeared on distant horizons, before rats, cats, and pigs stepped onto isolated shores, many islands had already served as stages for evolutionary experiments even stranger than these. There were places where birds did not merely give up flight. They grew so large that they became true giants, ruling entire forests in the same way large animals ruled the continents. That is the next chapter of the story of islands where birds became the giants of a forgotten world. When we think of birds, the first image that usually comes to mind is a pair of wings spread across the sky. Birds seem so deeply tied to flight that it is difficult to imagine them any other way. A bird that cannot fly feels like an exception. A giant bird that cannot fly feels even more like a paradox. But on isolated islands, where oceans form invisible walls separating life from the rest of the world, many familiar rules begin to soften. Rats can become unusually large. Lizards can climb to the top of the food chain. And when it came to birds, evolution carried out an even bolder experiment. It took the descendants of birds that had once crossed vast oceans on their wings and gradually transformed them into creatures that no longer needed the sky. They lived on the ground. They walked instead of flew. Generation after generation, they grew larger until they became the giants of entire ecosystems. In New Zealand, before the arrival of humans, the forests looked very different from those of the great continents. There were no herds of deer grazing beneath the canopy, no bison wandering through valleys, no large herbivorous mammals shaping the landscape. That empty role was filled by birds. In that world emerged the moa, a group of flightless birds found nowhere else on Earth. Over spans of time so vast, they are difficult to comprehend within a human lifetime. Their bodies became larger and larger. Their legs grew stronger to support increasing mass. Their wings gradually shrank until they almost disappeared entirely. The largest members of this group could make anyone standing beside them feel small. Adult females of the South Island giant moa could reach foliage more than 3.5 meters above the ground. Weighing over 200 kilograms, they ranked among the tallest birds ever to exist. What is remarkable is that moa were not fearsome predators. They did not rule the forest with claws or sharp beaks. Their lives unfolded at a much slower rhythm. Day after day, those enormous bodies moved through valleys, browsing leaves, feeding on shoots, swallowing fruits, and unintentionally carrying seeds across the landscape. In a sense, they resembled giant deer wrapped in feathers more than what we usually think of as birds. The entire forest seemed to adapt to their presence. Trails formed beneath their heavy footsteps. Seeds spread along their feeding routes. The vegetation of many regions was shaped by the habits of these giants. A creature whose ancestors once flew across oceans had become one of the largest animals on an entire island. On the other side of the Indian Ocean, another island was conducting a similar evolutionary experiment, but on an even grander scale. Madagascar had long existed as a world apart. Millions of years of isolation created opportunities for countless unusual forms of life. Among them was a group of birds that made even the moa seem modest by comparison. These were the elephant birds. Some species stood nearly 3 meters tall and weighed between 450 and more than 600 kilograms. To appreciate the difference, even a large modern ostrich weighs only a fraction of what the largest elephant birds did. At that size, the very idea of a bird begins to feel unfamiliar. They no longer resembled creatures built to conquer the sky. They looked more like immense feathered masses moving slowly through Madagascar's ancient forests. The most famous wonder they left behind was not a skeleton or a footprint, but their eggs. A single elephant bird egg could hold a volume equivalent to well over 100 chicken eggs. Placed beside an adult human, it looked more like a large vessel than an egg in the ordinary sense. It was one of the largest biological structures ever produced by a bird. Like the moa, elephant birds were primarily plant eaters. They moved through vast forests, influencing where plants grew, shaping patterns of regeneration, and leaving ecological footprints across enormous areas. The moa of New Zealand and the elephant birds of Madagascar never met. Thousands of kilometers of ocean separated them. Yet both tell the same story. When similar conditions arise, evolution can sometimes arrive at remarkably similar solutions. The distant ancestors of both groups belong to lineages of flying birds. That makes the question especially fascinating. Why would such a powerful ability as flight be abandoned? The answer lies in biological cost. Flight is one of the most energy-demanding activities in the animal kingdom. To maintain that ability, birds require powerful chest muscles, lightweight skeletons, and exceptionally high metabolic rates. All of these demand enormous amounts of energy every day. On many ancient islands, that pressure diminished dramatically. There were fewer predators, less competition, vast ecological opportunities waiting to be filled. When birds no longer needed to take flight constantly to escape danger, the energy once devoted to flying could be redirected elsewhere. Larger bodies, greater energy reserves, more effective foraging. Over time, size became more valuable than wings. On continents, evolution often rewards creatures that can fly farther or faster. On islands, the reward sometimes goes to creatures that no longer fly at all. Even so, islands are not machines that always produce giants. Many island birds remain small. The kiwi is one famous example. Numerous rail species lost the ability to fly without developing massive bodies. Others followed entirely different paths of adaptation. This reveals an important truth. There is no fixed formula. Every island is a unique set of conditions. Every ecosystem presents a different problem to solve. What evolution amplifies is not a particular shape, but the opportunities created by the environment. Perhaps that is the most thought-provoking lesson of all from these feathered giants. We often think of flight as the defining essence of birds. Yet the moa and the elephant bird suggest the opposite. Flight is not destiny. It is simply one solution that happened to work well under certain circumstances. When circumstances change, the solution changes as well. Many traits we regard as permanent features of life are, in reality, temporary responses to particular environments. Adaptation is not loyal to tradition. It is loyal only to what works in the present moment. On those isolated islands, circumstances changed so profoundly that even the sky itself was no longer necessary. But birds were not the only group to take advantage of the ecological opportunities islands created. Elsewhere in the world, a lineage even older was quietly stepping back toward the center of the evolutionary stage. Not mammals, not birds, but the surviving descendants of a far more ancient age, when reptiles once ruled the world and had never fully surrendered their throne. Imagine a place where no lion's roar rolls across the grasslands, where no tiger moves like a shadow through the forest, where no pack of wolves pursues its prey beneath the fading light of sunset. The familiar predators of the continental world are entirely absent, and yet a food chain cannot simply end in emptiness. Every ecosystem needs a summit, a creature that helps regulate the life beneath it. By now, we have traveled across islands where rats grew into giants, where elephants shrank to astonishing sizes, where birds abandoned the skies their ancestors once ruled, and where a lizard rose to become the terror of an entire archipelago. At first glance, these stories seem unrelated. In reality, they're all pieces of a much larger picture. That picture lies in the quiet way islands reorganize entire ecosystems. From the Galapagos in the Pacific Ocean to Aldabra off the coast of Seychelles, from Komodo in Indonesia to the ancient islands of the Caribbean, the same pattern appears again and again. Reptiles are no longer supporting characters. They step into the center of the stage. On vast continents, reptiles must share the world with countless powerful rivals. Big cats dominate the top of the food chain. Wild dogs hunt in coordinated packs. Bears rule across many different habitats. Large herbivorous mammals shape landscapes through their sheer size and abundance. Most of the key positions in the ecosystem are already occupied. Islands tell a different story. Many islands formed in such deep isolation that large mammals never managed to reach them. Others once had them, only to lose them through shifts in climate or the slow upheavals of geological history. When that happens, strange gaps begin to appear in the ecosystem. The apex predators are gone. The dominant grazers disappear. The animals that spread seeds across great distances or reshape habitats through their daily activities are no longer there. Nature rarely leaves an empty seat vacant for long. Sooner or later, something else steps forward to take it. On many islands, the creatures given that opportunity were reptiles. One of the most striking examples can be found in the Komodo archipelago. Across the dry landscapes of Komodo, Rinca, Flores, Gili Motang, and Gili Dasami, a giant lizard stepped into a role that people usually associate with lions or jaguars. The creature is the Komodo dragon, stretching beyond 3 meters in length and built with powerful muscles. It moves across sunburnt hillsides like a true ruler of the land. It ambushes Timor deer, hunts wild pigs, and attacks young or weakened water buffalo. There are no large cats competing for its prey, no sizable hunting dogs challenging its dominance, none of the familiar rivals found on the mainland. An ecological vacancy gave the Komodo dragon a remarkable role. It became the apex predator of an entire ecosystem. Realizing this creates a strange sense of wonder. Islands do not always produce miniature versions of the worlds we know. Sometimes they create entirely different worlds, where a giant lizard holds the kind of power that belongs to large predatory mammals elsewhere. Yet the road to power is not always paved with predation. Far out in the Pacific, other giants shape their worlds in a far quieter way. Galapagos giant tortoises can live for more than a century. They move so slowly that time itself seems to slow around them. At first glance, they appear to be gentle herbivores, spending most of their lives searching for leaves, fruits, and low-growing plants. But every step they take leaves a mark on the future of their island. As they feed, they open gaps within dense vegetation. As they travel, they create pathways that countless other animals use. When they eat fruit and carry seeds through their digestive systems, they unknowingly become gardeners for the next generation of plants. In many cases, the forests of the future begin with the slow journey of an old tortoise. Their influence is so profound that they are often considered ecosystem engineers. They need no sharp claws and no frightening speed. Yet they can reshape the landscape around them all the same. On the far side of the Indian Ocean, on the coral island of Aldabra in Seychelles, a close relative performs a similar role on an even larger scale. Aldabra is home to the largest surviving natural population of giant tortoises on Earth. Tens of thousands of individuals move slowly across grasslands and shrublands that stretch towards the horizon. They disperse seeds, shape the structure of vegetation, and influence countless other organisms sharing the same habitat. On many continents, such work is carried out by vast herds of mammals. On Aldabra, it is done by tortoises. Gradually, a larger pattern begins to emerge from all these seemingly unrelated examples. On continents, mammals often occupy the most powerful positions in an ecosystem. On islands, that rule is no longer guaranteed. The Komodo dragon becomes the apex predator. Galapagos tortoises become ecosystem engineers. Aldabra tortoises become the primary seed dispersers. Each species takes on a role once filled by entirely different groups of animals. Evolution does not care who occupied a throne in the past. It does not care about reputation, ancestry, or history. The only thing that matters is how well a creature fits the opportunity that exists. That is why the thrones of nature have never belonged to permanent rulers. They belong only to the organisms best adapted to the world as it exists at that moment. So far, The changes we have seen are easy to recognize. Some species grow larger, others become smaller. Some lose the ability to fly. Others transform into giant predators. But evolution on islands has never stopped. Even now, on the windswept islands off the coast of Scotland, new changes are unfolding generation by generation. They do not produce giant monsters or strange creatures obvious at first glance. They are smaller, subtler, almost invisible within the rhythm of everyday life. And yet these quiet transformations may be telling us something remarkable. The long-running experiment of the islands is still underway, and a new chapter of evolution may already be beginning in our own age. If evolution is still at work, can we actually see it with our own eyes? Or do all its traces now belong only to ancient rock layers, fossilized skeletons unearthed from the ground, or the memory of creatures that disappeared long ago after traveling through stories of giant island rats, miniature elephants, flightless dodos, the colossal moa of New Zealand, Madagascar's elephant birds, and the Komodo dragon? It is easy to feel as though the strangest evolutionary tales belong entirely to the distant past. Yet in the northern Atlantic, among the cold seas surrounding Scotland, a different story is unfolding. Shetland lies to the north. St. Kilda sits far to the west, separated from the mainland by stretches of wind-swept ocean. Winters linger here. Storms repeatedly batter the cliffs. The chill of the sea finds its way into every crack and crevice. There are no giant creatures here to inspire awe, no fearsome predators. The central character of this story is a bird so small that most people could walk right past it without ever noticing. It is the Eurasian wren, troglodytes troglodytes. On the British mainland, an adult typically weighs between 7 and 10 grams. Its body is so small that it can rest comfortably in the palm of a human hand. That modest appearance contrasts sharply with the powerful song that emerges from its tiny chest. Among low shrubs and ancient stone walls, its voice often seems far larger than its size would suggest. For many years, this bird appeared to hold no great mystery. It was too familiar, too common, too small to become the subject of grand evolutionary stories. Then, careful measurements of the population living on St. Kilda began to reveal something unexpected. The wrens here no longer match the familiar size of their mainland relatives. Many individuals weigh between 13 and 16 grams. Some of the largest birds are nearly twice the weight of the smallest wrens found elsewhere in Scotland. This difference is no longer a matter of random variation between individuals. It reflects a trend unfolding across an entire population. That raises a fascinating question. Why is a tiny bird following a path similar to the one that once turned island rats into giants and pushed many reptiles far beyond the size of their ancestors? Could the same rule that shaped islands thousands of years ago still be operating in the modern world? To find the answer, we must travel back to the first generations of wrens that reached the remote islands off Scotland's coast. They may have arrived from mainland Scotland or from nearby regions of northern Europe. At first, the separation between populations was not especially dramatic. A bird could still cross the sea. A wandering individual could still find new land. Over time, however, the ocean became an invisible boundary. Movements between island and mainland grew increasingly rare. The flow of genes that once connected populations began to weaken. Each small island gradually became its own world, with its own conditions, challenges, and opportunities. Shetland is different from Fair Isle. Fair Isle is different from the Outer Hebrides, and St Kilda is different from all of them. Each island resembles an independent experiment quietly conducted by nature. No massive walls or mountain ranges are required. Sometimes a stretch of sea, only a few dozen kilometers wide, is enough to send two populations down entirely different evolutionary paths. Yet isolation was only the beginning. A stronger force lay in the harsh climate of the North Atlantic. On St Kilda, strong winds blow through most of the year. Cold rain is a constant companion. Long winters create relentless survival pressures for small animals. For a bird weighing only a few grams, body heat is as precious as the last fuel remaining during a stormy night. A larger body offers several unexpected advantages. It retains heat more efficiently. It stores more energy. It allows an individual to endure longer periods of food scarcity before reaching a dangerous threshold. In such an environment, birds that survive winter even slightly more often gain a significant advantage. Across hundreds of generations, those small differences accumulate. No goal is set in advance. No plan exists to create larger birds. Individuals simply better suited to their environment have a greater chance of passing their traits to the next generation. Over time, the average size of the population gradually increases. What makes this especially interesting is that the advantage depends entirely on context. On the mainland, being small and agile may be an effective strategy. On cold islands surrounded by the sea, a larger body becomes the better solution. The same species, living in two different environments, is writing two different versions of the future. Size is only the most visible change. Deeper transformations are occurring across multiple layers of biology. Beak shape has begun to diverge. Body proportions are shifting. Certain plumage traits are no longer quite the same as those found in mainland populations. These changes are subtle enough to escape casual observation, yet together they form a very different picture. Even the songs are changing. The melodies carried across the isolated cliffs of Shetland and St Kilda are not exactly the same as those heard on the mainland. Over time, these songs become distinctive signatures. Each population seems to be developing a voice of its own. Deeper still lie differences hidden within the genome. Genetic data reveal that island populations are now significantly separated from their mainland ancestors. The divergence no longer exists only in appearance or behavior. It has been recorded within the genetic code itself, passed from one generation to the next. That is where the story becomes truly remarkable. The St Kilda wren and the Shetland wren are still considered subspecies of the Eurasian wren. They are not yet entirely separate species. Yet the distance between them and the mainland population continues to grow more apparent. Many famous species from evolutionary history began in exactly this way. The dodo did not appear in a single moment. The moa did not appear in a single moment. The Komodo dragon did not appear in a single moment. Every great difference begins with small changes that almost nobody notices. Perhaps the most astonishing thing is not that these birds are growing larger. The astonishing part is that they allow us to observe evolution in real time, not through fossils, not through stone-preserved skeletons, not through creatures that survive only in books. These changes are happening in living animals, flying through the cold winds of the North Atlantic right now. When we look at an island, We often think we are looking at a place separated from the rest of the world. Yet from the perspective of evolution, every island resembles a time machine. What may take tens of thousands of years to become visible elsewhere on Earth can sometimes emerge much sooner on these isolated fragments of land. The small birds of Scotland today may represent only the opening chapter of a very long story. A story that, thousands of years from now, people may call by another name and recognize as another species. Because a new species is never born in a single day. It is built from countless tiny differences, accumulating quietly through time. Size is only the first sign. More subtle changes are already echoing among the cliffs facing the cold sea. They exist in sounds that other wrens can recognize, but humans barely notice. They exist in the way individuals choose mates and identify members of their own population. Sometimes the beginning of a new species is not a different shape at all. Sometimes it begins with a different song. What happens when a bird no longer sings like its ancestors? Imagine two birds perched on opposite branches. They share the same plumage, the same size, the same shape of beak. To the human eye, there is almost no reason to think they are different. But when one begins to sing, the other does not answer. A sound that was once a common language between them has become something unfamiliar. Up to this point, our journey has mostly revolved around changes we can see: mice growing larger, elephants becoming smaller, birds abandoning the sky, reptiles rising to dominance. Yet evolution does not work only on bodies. It also reshapes the ways living creatures communicate with one another. And sometimes those invisible changes carry more power than any transformation of form. Across islands scattered from Scotland to the Galapagos, from Hawaii to the Azores, bird populations isolated for long stretches of time have begun developing their own distinct signals. In this story, the main character is no longer a wing or a beak. The main character is sound. For many birds, a song is far more than a melody drifting through the landscape. It is how they recognize members of their own kind, attract mates, defend territory, and distinguish who belongs within their community. More remarkably, many species are not born knowing how to sing. They must learn, much like children learning language from those who came before them. A birdsong is therefore both a biological trait and a cultural inheritance, passed from one generation to the next. When a group of birds reaches a distant island and becomes separated from its ancestral population, change begins quietly. They live among different forests, different mountains, different winds. Sound moves through the new environment in ways it never did before. Certain notes become longer to carry through dense vegetation. Some phrases grow shorter to cope with echoing terrain. Certain tones are repeated more frequently than others. At first, the differences are almost impossible to notice. Young birds learn these slightly altered versions. They then pass them on to the next generation, year after year, generation after generation. Tiny variations accumulate like thin waves continually layering themselves upon a shoreline. After hundreds or thousands of generations, the island song no longer resembles the song once heard in the homeland of its ancestors. But the changing soundscape is only the surface of the story. In many bird species, females tend to prefer familiar songs, the sounds they learned to recognize when they were young. When populations remain separated long enough, each group gradually develops its own local accent, much like regional dialects in human language. Then a strange paradox appears. The two populations still share a common ancestor. They may still look remarkably alike. They may even remain biologically capable of mating with one another. Yet they slowly stop seeing each other as ideal partners, not because their feathers changed, not because their beaks evolved into different shapes, simply because the song became different. Birdsong becomes an invisible wall, separating populations long before their bodies have changed in any obvious way. This process is unfolding in many places around the world. In the Galapagos, populations of Darwin's finches living on different islands have developed distinct song patterns. Males often respond more strongly to the familiar songs of their own island, as though recognizing a familiar voice among a crowd of strangers. In Hawaii, several isolated honeycreeper populations have gradually formed their own unique song structures. These differences persist not through genes alone, but through social learning repeated across generations. Off the coast of Scotland, populations of wrens living on different islands appear to be following similar paths. Not only are size and physical form showing signs of divergence, their sounds and methods of communication are slowly drifting apart as well. When we think about evolution, we usually imagine dramatic and visible transformations. A pair of wings disappears, a body grows enormous, an entirely new form emerges. But nature rarely begins with revolutions that loud. Sometimes the first step towards separation is nothing more than a few notes sung differently, a sound no longer recognized, a call that no longer receives an answer, a song that no longer leads to a mating pair. From that moment onward, two evolutionary paths have already begun to diverge. When we look at a species, we often assume its identity resides in its feathers, its beak, or its wings. Yet in many cases, what truly shapes the future of a population is a set of invisible signals that allow individuals to recognize one another within a vast world. A new species does not always begin with a new shape. Sometimes, it begins with a new song. And if only a handful of different notes can alter the destiny of an entire population, then the next question becomes almost impossible to avoid. What is it about islands that keeps producing changes like these? Why do similar patterns appear again and again in mice, in birds, in reptiles, and even in songs carried across the ocean wind? Perhaps islands hold a special evolutionary formula, one that has been quietly at work for millions of years, and one that we are only beginning to see. After traveling across islands scattered throughout different oceans, a question begins to emerge more clearly than any creature we have encountered so far. Why do the same strange patterns keep appearing in places completely cut off from one another? A rodent on Caribbean islands evolves toward gigantism. An elephant in the Mediterranean follows the path of dwarfism. A bird in New Zealand abandons the sky. A reptile in Indonesia rises to dominate its ecosystem. There is no direct connection between them. They do not share a recent evolutionary history. They do not live in the same climate, among the same vegetation, or within the same biological communities. Yet the outcomes are astonishingly similar. Rodents grow enormous. Elephants become miniature. Birds lose the power of flight. Reptiles expand their ecological roles. Isolated bird populations begin singing songs their ancestors never knew. At first glance, these seem like separate stories. But the farther we step back to view the entire picture, the more it becomes clear that they are all expressions of the same underlying mechanism. In this chapter, the main character is no longer the dodo, the moa, the Komodo dragon, or any other animal. The main character is the island itself. The first ingredient in the formula begins with an absence. Many oceanic islands formed far from continental land masses. Reaching them was already an extraordinary challenge. Animals capable of long-distance flight or accidental journeys on ocean currents sometimes made it there. But for large predators, specialized carnivores, or species that required vast territories, the journey was often nearly impossible. As a result, many islands emerged with far fewer predators than comparable environments on the mainland. Pressures that had shaped life for millions of years suddenly weakened. And that is where an important phenomenon appears, often called ecological release. When fear is no longer present with the same intensity, many traits that were once essential for survival begin to lose their value. A bird no longer has to take flight constantly to escape ground predators. A rodent no longer spends most of its life in a state of vigilance. A reptile is no longer overshadowed everywhere by larger mammals. The dodo is a familiar example. So is the kakapo. Flightless rails evolved repeatedly on different islands despite having no close relationship to one another. Rodents across multiple archipelagos grew to unusual sizes, not because they shared some secret evolutionary blueprint, but because they were responding to the same ecological conditions. Yet fewer predators are only part of the story. On continents, species often exist within crowded ecosystems. Dozens or even hundreds of species compete for food, shelter, and reproductive opportunities. Each occupies only a small piece of a much larger picture. Islands are often different. Many ecological roles remain unfilled. No species occupies them. No competitor is waiting to defend them. These vacant spaces become evolutionary opportunities, allowing a species to expand far beyond the limits it once knew. New Zealand was once a remarkable example. Before humans arrived, the islands had almost no large land-dwelling, herbivorous mammals. That ecological vacancy did not disappear. It was filled by the moa. These flightless birds, standing more than 3 meters tall, came to occupy a role that elsewhere would usually belong to deer or other large grazing mammals. In Indonesia, the story unfolded in a different direction. Across much of the world, the role of apex predator is typically held by mammals. But on some islands of the lesser Sunda chain, the Komodo dragon expanded its role dramatically. It became more than just a giant lizard. It became one of the dominant predators of an entire ecosystem. Islands do not create creatures out of nothing. They offer creatures new jobs. Evolution then begins reshaping bodies, behaviors, and lifestyles to match those jobs. That is the essence of adaptive radiation and the ecological transformations that unfold across generations. Yet the most important ingredient in the formula may be the one we can barely see. It is the restriction of gene flow. On continents, populations constantly receive new genes from neighboring groups. A new trait that appears today may be diluted tomorrow by countless incoming genetic influences. The system resembles a mixture that is continually being stirred. On islands, the ocean acts as a massive wall. The greater the distance, the harder that wall becomes to cross. New traits that emerge within a population are less likely to be erased. They have more opportunities to accumulate through time. That is why the wrens of St. Kilda gradually diverged from their mainland relatives. It is also why bird songs on islands continue changing generation after generation. Small variations in sound, behavior, or form are given more time to persist and become increasingly pronounced. Evolution on islands is not necessarily faster. The difference is that change has a greater chance of being preserved. When isolation becomes strong enough, returning to the previous state becomes increasingly difficult. Modern research also suggests that not all islands produce the same effects. Two factors appear especially important: island size and distance from the mainland. The smaller the island, the more limited its resources. The farther the island, the stronger its isolation. When these two conditions combine, the island rule becomes most visible. Island gigantism appears more strongly among many small animals. Island dwarfism becomes more pronounced among many large animals. Specialization deepens as well. The dodo of Mauritius, the moa of New Zealand, giant rodents from ancient islands, and the many birds that repeatedly abandoned flight all reflect the same pattern. Fewer predators, fewer competitors, less gene flow. At this point, the entire picture begins to come together. What once seemed almost surreal now becomes easier to understand. Giant rodents are not miracles. Dwarf elephants are not exceptions. Flightless birds weighing hundreds of kilograms are not mistakes of nature. The dominance of the Komodo dragon is not mysterious. Even the emergence of new songs that gradually create new biological boundaries is simply the result of familiar rules operating under unusual circumstances. Natural selection remains natural selection. The only thing that changes is the room in which it operates. On continents, evolution resembles a vast river with countless branches that constantly meet, merge, and separate. On islands, evolution resembles a narrow path stretching through an immense ocean. Every step is less influenced by the outside world. Every small change has more time to survive. Every new difference has more opportunity to deepen. Isolation does more than change the shape of life. It changes the direction of life. Many of the traits we think of as the essential nature of a species are, in reality, simply responses to pressures that species faced in the past. When those pressures disappear, evolution is ready to rewrite the story from the beginning. But isolation always carries a cost. The more perfectly a species adapts to an island, the more tightly its fate becomes tied to that island. When its entire world exists on a small piece of land surrounded by ocean, every disturbance grows larger. Every change becomes more serious. Every mistake becomes more dangerous. And it is here, in the very places where evolution creates its greatest wonders, that nature's most fragile destinies also begin to take shape. What happens when the entire fate of a species rests on just a handful of small islands in the middle of the ocean? Up to this point, our journey through the islands has seemed like a series of evolution's strangest triumphs. Rats grew into giants. Elephants shrank into miniature versions of their ancestors. Birds abandoned the sky, yet continued to survive for thousands of generations. Reptiles stepped into ecological roles that, elsewhere, are usually filled by mammals. Each of these stories feels like proof of nature's almost limitless creativity. And yet, the longer we look, the more a paradox begins to emerge behind those successes. Many of the most successful island species are also among the most vulnerable. Creatures that seem to have discovered the perfect formula for survival in their environment often face the greatest risks when that environment begins to change. No animal illustrates this more clearly than the Komodo dragon. From a distance, the Komodo dragon appears to be an unshakable ruler. Its immense body, formidable strength, position as an apex predator, and worldwide reputation make it seem almost invincible. But look at a map, and that empire suddenly becomes astonishingly small. The natural world of the Komodo dragon exists only across a cluster of islands in Indonesia: Komodo, Rinca, Flores, Kilimotang, Kilidasami, a handful of volcanic islands scattered across the sea, separated from the rest of the world by vast stretches of water. If they were wolves, they could roam across national borders. If they were leopards, they could control territories stretching across hundreds of square kilometers. But for Komodo dragons, their entire evolutionary history, their entire future, and nearly every opportunity for survival are contained within a remarkably small corner of the ocean. It is here that, over hundreds of thousands of years, they learned to read their world. They know where Timor deer are most likely to appear during the dry season. They know which areas retain moisture after months of relentless heat. They know the right moments to hunt and the landscapes most likely to support life within Wallach's harsh and dry ecosystems. Komodo dragons did not become apex predators because they are the strongest animals on Earth. They reached that position because they became almost perfectly tuned to the environment they inhabit. But evolution has a very particular limitation. It always responds to the past. It cannot see the future. For most of a species' history, environmental change happens slowly. A forest might shift over thousands of years. An ecosystem might transform across tens of thousands. Populations had time to adapt through countless small steps. Modern pressures move to a completely different rhythm. Much of the Komodo dragon's habitat lies in lowland areas where dry savannas meet coastal landscapes. These are also among the places most vulnerable to rising temperatures and sea levels. As shorelines change, portions of habitat may shrink. As climates shift, the distribution of vegetation, water sources, and prey species changes as well. The concern is not a single event, it is the speed. A world that once changed over millennia can now transform within only a few generations. The next pressure comes from the food web itself. Komodo dragons depend heavily on medium-sized hoofed animals, such as Timor deer and wild pigs. When prey populations decline, the effects do not stop at one link in the chain. They ripple throughout the entire ecosystem. Small changes at the lower levels eventually reach the predator standing at the very top. Then comes human pressure. Roads appear. Infrastructure expands. Tourism grows. Landscapes that remained relatively stable for long periods begin changing more rapidly. Encounters between humans and wildlife become increasingly common. Pressures this species never experienced through most of its evolutionary history slowly become part of everyday reality. What is remarkable is that the Komodo dragon is far from alone in this story. Off the coast of California, a small fox evolved successfully on isolated islands. For thousands of years, it adapted perfectly to its environment. Then a new threat arrived. Golden eagles began hunting it. Within a short period, several populations declined until only a few dozen individuals remained. Not because they were weak, not because they had failed, but because their evolutionary history had never prepared them for that challenge. Far out in the Pacific, many Hawaiian honeycreepers now face a similar paradox. They survive in increasingly restricted, high-elevation habitats. As temperatures rise, disease-carrying mosquitoes expand into new areas. Places that were once safe refuges gradually become more fragile. In Madagascar, many native carnivores and endemic primates now persist only in fragmented pockets of forest. As forests are divided, their world becomes divided as well. Populations that were once connected become isolated into biological islands surrounded by a sea of human activity. These stories unfold in very different places. The animals involved are very different too, yet they all lead toward the same conclusion. Evolution is not only a story of victory. The islands reveal another side that receives far less attention. The more perfectly a species adapts to one place, the more dependent it becomes on that place. A migratory bird can cross oceans in search of a new environment. A wolfpack can expand its territory across hundreds of kilometers when food supplies change. But some island species live in worlds no larger than a small city. The very traits that once made them successful gradually become invisible threads, tying them to their homeland. Adaptability was once the key that opened the door to survival. Over time, that same key can sometimes become the lock. Imagine a major wildfire sweeping across an island, an unusual storm making landfall, a new disease spreading through the landscape, or simply a small shift in available food resources. For many continental species, such events may be only local hardships. Other regions remain available. Other populations continue to exist elsewhere. For many island species, however, that may be the entire world, the entire habitat, the entire history, the entire future. The Komodo dragon embodies this paradox with remarkable clarity. It is an apex predator. It possesses extraordinary strength. It stands as a symbol of evolutionary success on islands. Yet its entire empire exists on only a few small islands surrounded by sea. Power and fragility coexist within the same body. Not every evolutionary story ends in triumph. Sometimes, nature creates creatures so perfectly adapted that they no longer fit anywhere except the place that shaped them. Specialization opens a path to survival. At the same time, it quietly narrows the routes of escape. And perhaps the most sophisticated cage in nature is not built from claws, fangs, or predators. It is built from success itself. But this is not the end of the story of islands. While some species struggle to hold their place, other islands continue doing what they have done for millions of years. They continue isolating populations. They continue creating new pressures. They continue experimenting with genes in ways that few other places on Earth can. And somewhere across the vast ocean, the next strange creatures may already be beginning to emerge. Right now. After a long journey through fossil skeletons, birds that vanished from the sky, and creatures that now survive only in the memory of stone, it is easy to fall into a familiar feeling. the feeling that all those strange wonders belong to a world that ended long ago. The dodo is gone. The moa is gone. Madagascar's elephant birds remain only as enormous fragments of bone. Even many of the creatures that once dominated island ecosystems now exist only in ancient layers of sediment. But islands never stop doing their work. They continue to separate small populations from the rest of the world. They continue to create unique environments with unique survival pressures. They continue to select, experiment, and shape life in directions that the mainland rarely repeats. The only difference is that this time, we're here to watch the process as it unfolds. Off the western coast of Scotland, the St. Kilda archipelago rises from the North Atlantic as a collection of lonely cliffs surrounded by sea. Ocean winds, cold rain, and isolation have shaped these islands for countless generations. Among them lives a small population of wrens, known as the St. Kilda wren. At first glance, there seems to be nothing remarkable about them. They are still small brown birds hopping through low vegetation and among rocky coastal slopes. Yet when they are compared with their relatives on mainland Britain, differences begin to emerge. Their bodies are noticeably larger. An adult individual can weigh nearly twice as much as a mainland wren. Size is not the only change. Body proportions, structural features, and many genetic characteristics are gradually drifting away from the ancestral population. A quiet process of genetic divergence is accumulating generation after generation without making a sound. These changes remind us that island evolution does not always produce giant monsters overnight. Sometimes it begins with differences so subtle that they are almost impossible to notice within a single breeding season. Farther north, in the Shetland Islands, evolution is working on an even deeper level. Here, wren populations are changing not only in body form, but also in sound. Birdsong is not fixed. Each generation learns its melodies from the one before it. During that process, small variations appear and slowly accumulate over time. After many generations separated by the sea, Shetland wrens have begun to develop songs that carry their own distinct identity. These songs are like biological dialects. They are invisible and cannot be seen with the eye, yet they can influence recognition, mate selection, and gene flow. A new species does not necessarily begin with different wings or different colors. Sometimes speciation begins with a different melody carried by the wind. From the cold islands of the North Atlantic, the journey takes us to the equatorial waters of the Eastern Pacific, where the Galapagos Islands continue to demonstrate that evolution can move far faster than human intuition suggests. Darwin's finches have become one of the most famous symbols of evolutionary biology. What makes them extraordinary is not their appearance, but the astonishing speed at which they can change. During drought years, when soft seeds become scarce and larger, harder seeds dominate the landscape. Individuals with larger beaks have a better chance of surviving. After only a few generations, the average beak size of the population shifts in a new direction. When environmental conditions change again, the direction of selection changes with them. These transformations are not inferred from fossils millions of years old. They have been recorded while unfolding in front of scientists' eyes. In the Galapagos, adaptive radiation continues to operate. Small finch lineages are still testing new survival strategies under the pressures of climate and food availability. Evolution is no longer a story from the distant past. It is happening in real time. But sometimes islands produce something even stranger. They do not simply create new solutions. They create the same solution again and again. In Cuba, Hispaniola, Jamaica, and Puerto Rico, the ancestors of anolis lizards arrived on different islands long ago. They were then separated for millions of years and evolved independently. By simple logic, each island might have been expected to produce entirely different outcomes. What actually happened is far more remarkable. On every island, evolution repeatedly produced strikingly similar body forms. There are always species specialized for life high in the canopy. There are always species adapted to tree trunks. There are always species that spend most of their time near the ground. There are always tiny species that live among slender branches. These evolutionary lineages did not directly give rise to one another. They are independent experiments. Yet nature repeatedly arrives at similar answers to the same problem. This is one of the most elegant examples of convergent evolution, where very different paths lead to remarkably similar destinations. All of these modern observations point toward the same realization. Islands are still producing larger bodies. They are still producing smaller bodies. They are still producing new songs, new behaviors, new shapes, and populations that grow increasingly distinct from one another. Not every change ends with the birth of a new species, but every species that has ever appeared on Earth began with small changes like these. When we look at an island bird population today, we may be looking at the ancestor of a species that does not yet exist, a new evolutionary branch still in its earliest stages, a draft that life continues to revise with every passing generation. People often associate evolution with museum skeletons or fossils buried deep beneath the ground. Islands tell a very different story. They reveal that evolution is not a memory. It is a process unfolding all around us, slow enough to be difficult to notice within a single lifetime, yet powerful enough to alter the destiny of an entire lineage across many generations. And that brings us to the final question of this journey. When we call the dodo, the moa, the Komodo dragon, or those giant wrens the monsters of islands, are they truly strange at all? Or are they simply creatures that lived long enough in isolation to become a different version of themselves, a version that the mainland never had the opportunity to create? (8.15) Monsters are not strange creatures. They are creatures shaped by isolated time. After traveling through islands scattered across the world's oceans, we have encountered creatures that seem as though they belong to a different reality. A rat on Flores, nearly the size of a cat. Dwarf elephants that once walked across Mediterranean islands. The dodo of Mauritius. The moa of New Zealand. The giant elephant birds of Madagascar. Komodo dragons ruling island kingdoms of their own. Tiny wrens on St. Kilda, carrying the marks of isolation accumulated over countless generations. When faced with forms like these, humans often respond with the same word: monster. The word appears almost automatically when a rat becomes too large, when a bird stands taller than a grown person, or when a lizard rises to the top of the food chain. They break the patterns we are familiar with. They make the world feel stranger. Yet what is remarkable is that none of these creatures ever tried to become unusual. None of them deliberately set out to be extraordinary. No species chose to become a monster. They were simply responding to the environment around them, just as every living thing on Earth does. So what truly creates these seemingly bizarre forms? The answer does not lie within the animals themselves. The answer lies in the places where they remained for a very long time. Throughout much of this journey, our attention has focused on the dodo, the moa, and the Komodo dragon. But when we step back and look at the larger picture, the most important character has always been standing quietly behind every story. Isolation. Across vast continents, life exists within an enormous web of connections. Populations constantly exchange genes. Animals migrate from one place to another. Predators appear and disappear. Competitors change through time. Food sources shift from generation to generation. Every lineage is pulled by countless ecological relationships woven together into a complex network. An island operates differently. When the ocean creates enough distance, many of those connections begin to break. New genetic input becomes rare. Competitors become fewer. Predators become fewer. Opportunities to return to an earlier state become fewer as well. The outside world continues to change, but the island quietly preserves its own set of conditions. Small changes begin to accumulate. A slight difference in size, a slight difference in behavior, a slight difference in how a species feeds or survives. Across thousands, even tens of thousands of generations, those tiny differences build upon one another like invisible layers of sediment. Eventually, the result appears in the form of creatures that seem to outsiders as though they belong to another world. What matters is that these animals never took a wrong turn. On the contrary, they followed exactly the path their environment demanded. The dodo is a clear example. Its ancestors were flying pigeons capable of crossing oceans. When they arrived on Mauritius, they entered a world with almost no large terrestrial predators. Flight, one of the most energetically expensive abilities in the animal kingdom, gradually became less necessary. Over time, their bodies grew larger. Their ability to fly diminished. Eventually, the sky was no longer where they belonged. On the other side of the world, a different story unfolded according to the same rule. Ancient New Zealand lacked large grazing mammals such as deer and antelope. Those ecological roles remained vacant for a very long time. Certain bird lineages gradually began to fill them. Generation after generation, they grew larger. The final result was the moa, giant birds capable of standing more than 3 meters tall when stretching their necks. Sometimes, however, it was not birds that stepped into an ecological opportunity. In Indonesia's Lesser Sunda Islands, many mammalian predators were absent. Empty spaces emerged within the ecosystem. A lizard moved into one of those spaces and evolved into an apex predator. Over time, it became the Komodo dragon, the largest living lizard on Earth today. The dodo was not a failure of evolution. The moa was not a failure. The Komodo dragon is certainly not a failure. They are simply versions of life sculpted by island environments over long enough periods of time. Perhaps what makes them seem strange has little to do with them at all. If a person had been born on Mauritius before the first ships appeared on the horizon, the dodo would have seemed perfectly ordinary. If someone had grown up in New Zealand while moa still walked across grasslands and through vast forests, that sight would have felt completely normal. If you lived on Komodo Island, a 3-meter lizard would simply be another familiar part of the surrounding world. They never changed. Our perspective did. We call them monsters because they spent too long living in a different world, a world where the familiar rules of the mainland no longer applied, a world shaped by distance, isolation, and time. In the end, life has no fixed form. There is no standard size. There is no perfect body. Every shape is merely a temporary answer to the demands of a particular environment. Giant rats, dwarf elephants, flightless birds, lizards ruling entire ecosystems. All of them are different answers to the same question. What happens when life is separated from the rest of the world for long enough? Perhaps the answer has been waiting on those islands all along. The monsters of islands are not born from chaos. They are born when isolation lasts long enough for life to forget its original shape,